kind of summarize what we did in lab today. And of course, we started off with a little review of forces. We remembered that when there's no net force on an object, the object is either at rest or it's moving at constant velocity. That's where we are right now. And we have an equation for that. Basically, when there's no net force on the object, and of course by net force we mean that we are looking at all the forces combined, when an object's at rest or at constant velocity, all those forces combined, they equal 0. So in other words, the classic case that we have, and that's actually what kind of leads us into the lab, is when you've got, say, a normal force and you've got a weight, right, for an object that's standing perfectly still. We've done this a lot of times. What we say is, oh yeah, well, we know that the weight happens to be equal to the normal force. And we've been writing this a little bit differently lately. What we've been saying is, well, wait a minute, the normal force points up, the weight wants to pull the object down, and the effect is that these two forces cancel. That's where we're at right now. Through a little bit of thought and thinking about our lab and looking at what we did, what we realized is in a system where forces are imbalanced, what happens to the object is that it speeds up, slows down, or it stops. And the thing in physics is, you might think, if we were speaking casually, that speeding up, well, that's accelerating, and slowing down is decelerating, and stops, well, that's just stopping. In physics, we all give this one word. We call all three of these things acceleration. Now, some of you bright folks remembered that, or maybe you just read a lot of physics, read over your notes a little bit. You also remember that changing direction is also something that can happen to the object. But we're going to focus this next week on acceleration, meaning your speed changes. You speed up, slow down, or you stop. Now, in the lab that we did, we looked at the case of an elevator moving in a lot of different ways. So we had it starting at rest, and we drew free body diagrams for all of this. And we actually came up, and if you remember, we actually did this in class, so there's no need to repeat every single thing that we did. We had it starting at rest and accelerating upwards. And what we did was we said, well, look, when the forces are not balanced, we want to draw the arrows having a different length. So at rest and constant velocity, we knew that the normal force and the weight should have the same length. But in cases, say, where we're accelerating upwards, I'll just do this one right here. We want the arrows to clearly look like they have different length. And that's what we did in the pre-lab. Then what we did is we actually checked our predictions in lab. And as a result of checking our predictions, we came up with a completely new idea. And the idea that we came up with was simply this. And you know what? I'm going to write it in the pre-lab section just so we have it. What we came up with was the idea that when forces don't balance, the object accelerates. So in other words, the idea is, for this specific lab, I've got a normal force pointing up, I've got a weight pointing downwards, and when those two forces, so again, normal up, weight downwards, and when that elevator starts moving or stops moving, when when it just starts moving or it just stops moving, those forces no longer balance. And so the effect is, in fact, that the mass accelerates. And the way we write that is really, really simple. We take the mass and we times it by the acceleration. That's it. The general rule is, I'm going to write this as F net equals ma. This is the general rule. And we call this Newton's second law. And F net means you're adding up all your forces. And if they don't balance, they equal the mass times the acceleration. In other words, all those forces unbalancing makes your mass accelerate. It means speeds up, slows down, or stops. To really get this, what I want to do is I want to actually apply this to the lab problems that you have. So when you actually take your lab and you look at the Part 2 calculations, so we'll record our weight in pounds. So I actually weigh about 155 pounds. I'm a strapping young man. And we will actually convert this by using the conversion. 1 pound is 4.45 newtons. So and so if I have this right, I'm getting 690 newtons. Again, that's 155 times 4.45. And here we go. So in the case where the forces are balanced, let's actually write the equations for the forces. Now here we have the normal and the weight. And this we've done before. You can write it this way. You can write the normal equals the weight like we did last week. But I'm going to prefer now that we start talking about forces balancing and unbalancing this way. That when the forces balance, you actually subtract the weight from the normal, and those cancel like this. Okay, so this 0 means that they cancel. Now here's what happens. In the case where the forces are unbalanced, this right-hand side now reads as ma, and this is what's known as Newton's second law. So when they're balanced, it equals 0. When they're unbalanced, it equals ma, and that's the whole point of today's lab. And what that lets us do, that lets us calculate the normal force in a situation when the forces don't balance. So we want to figure out, well, what's the scale really reading, and what does that actually mean? So this is the kind of problem that we want to solve. It says if the elevator has an acceleration of 0.25 meters per second squared when it approaches the top, what is the magnitude of the normal force? So what we notice as we approach the top is that we actually felt lighter on the elevator. Okay. So what that means clearly is if we feel lighter, that means the normal force. That means if we feel lighter, what that means is the scale is reading lighter, and that means the normal force is less than the weight. So here's what I'll say. I will write the equation this way. I will say that the normal force going up minus the weight going down equals the mass times my acceleration. Now, if the weight's bigger than the normal force and I'm subtracting it, okay, we can actually realize here that this is going to be a negative acceleration. Okay, so that's going to be the tricky idea that we're going to talk about in class a little bit more. And so we can go ahead and calculate. So we have the normal minus, and my weight was given in newtons as 690. Equals m, so let's get my m. That's going to be weight divided by gravity, and that's going to be 690 divided by 9.8. And that's going to give me about 70 times negative 0.25. So sorry, I had a little video glitch there for a second. That is 70 times negative 0.25. So now I have the normal force equals 70 times negative 0.25 plus 690. So it looks like my normal force is less, which makes sense because my scale is lighter when I put it in those numbers. So that's going to give me 672.5 newtons. Now, what I'm going to have you do is try to take a look at number 4, 5 over the weekend, and then we'll look at these a little bit more in depth when we come back on Monday. So I want you to actually try to solve this and give your best guess. And what I'm going to do is I'm going to have you do these questions. So I want to look at them for completion, but we're going to actually take a look at these in more detail on Monday. So this is the hard part, figuring out why this negative sign is what it is. And then when we come back on Monday, we'll take a closer look at Newton's second law.